Today, we want to talk a little bit more about rational functions and specifically the graphs of rational functions. We want to make sure that while we're doing this, we connect things we see in the graph to things that we see in the function and things that we know about derivatives. We're trying to incorporate derivative thinking into what we already know, or maybe are expanding what we're learning about graphs of rational functions. So if you would recall, yesterday we talked about rational functions. The zeros of the denominator of a rational function will produce either a hole in the graph or a vertical asymptote. Vertical asymptote is the more interesting thing to happen, because a hole in the graph just means we cancel out a factor, and we can easily plug the hole in the graph by just canceling that factor and pretending that didn't happen. The interesting thing happens with vertical asymptotes. These are the very distinctive features of a lot of rational functions. There's also horizontal asymptotes for some rational functions. So the first thing that we notice is that x can't be zero. That's x can't be zero. That's a zero of the denominator. And in this case, since the x doesn't cancel out, we have a vertical asymptote at x equals 0. And we indicate a vertical asymptote with a dotted vertical line. The other thing that we noticed about this graph is that as x goes to infinity, this function goes to 0. So we have a horizontal asymptote we see a horizontal asymptote. Horizontal asymptotes mean that the function in the long run flattens out. So we have a horizontal asymptote. At y equals 0. We know what the graph of 1 over x looks like. So we get this hyperbola. We might not recognize it as a hyperbola. When we're drawing our hyperbolas, we want to make sure that our graph gets close to our asymptotes. So what I like to do is get my endpoints going, or not my endpoints, but give myself somewhere to aim and draw it almost horizontal and almost vertical, kind of around those corners, and then just connect those with the hyperbola in between. So what we want to emphasize, this is just style guide for drawing functions with horizontal or vertical asymptotes. You want to draw along the asymptotes, and you want it to be fairly close. I mean, I got this gigantic gap right here, but we're just trying to say we're headed towards that. We want to make it clear what we're headed towards. The other thing that we wanted to include with this is information about derivatives. So our function is an x to the negative 1. Our first derivative is negative x to the negative 2, or negative 1 over x squared. What we notice about the first derivative is that what we remember about the first derivative is that the sign of the first derivative tells us about the direction of the function. What we notice about the first derivative for this function is that it is always negative. If x is negative, the negative gets squared, and I multiply by this -1. If x is positive, the x gets squared and it's positive, and then we multiply by -1. So -1 over x squared is always negative as long as x is not 0, where it's undefined. That's our critical point. So this is negative for all x not equal to 0. So what that tells us is that the function should be decreasing for all x that's not 0. And that's what we see in the graph. When x is negative, the function is decreasing. When x is positive, the function is decreasing. We notice that the function is decreasing for all x, for all non-zero x. Nothing's going on at 0 because the function is not defined at 0. The other thing that we want to know is about concavity. And concavity we can determine with the second derivative. We can also look at the first derivative just based on the graph. And we can see that we have the function concave down when x is negative and concave up when x is positive. If we look at the slope is decreasing when x is negative. So here's a very flat slope, and the slope is becoming more negative. The number is getting bigger, but the value is negative, so it's decreasing. And then over here, we start with this really steep slope, and then the slope gets smaller. Or sorry, yeah. The slope here is negative, and it's becoming less negative. So that's increasing. Even though slope is gigantic, this gigantic negative number, which is less than a little tiny negative number. And we see that in the second derivative, because we get 2x to the -3. So the second derivative is 2x to the -3. In this case, we have the x to the -3. That can be positive or negative. The odd exponent is positive or negative depending on x. So 2 over x to the third is going to be negative when x is negative. And positive for positive x. Nothing's going on at 0 because the function is not defined at 0. And so the first and second derivatives are also not defined at 0. The sign of the second derivative tells us about the concavity of the function. So this tells us that f is concave down for negative x, and f is concave up for positive x. The reason that I picked this example is because we knew what this function looked like. This is what we want to think about when we're thinking about rational functions. We want to make sure that when we're thinking about functions, we remember what we know, and we incorporate the new stuff that we know into the old stuff. Yesterday I mentioned what are we going to do to move the vertical and the horizontal asymptotes. But the other thing that we wanted to point out, the thing that was emphasized yesterday, I wanted to look at the function 1 over x squared. this has a lot of similar features to the 1 over x. The difference is that this function is always going to be positive. And we want to see how that shows up. So 1 over x squared still has a vertical asymptote at 0 because we can't cancel out those x squareds. So that's not hole in the graph behavior. That is vertical asymptote behavior. Also, as x goes to infinity, 1 over x squared will go to 0. It'll go to 0 even faster. That's not the issue. The fact is that it's going to 0. The difference that we have here is that we're not going to have any negatives. So this negative stuff that we had in 1 over x becomes positive stuff, but the look is the same. We draw our graph close to asymptotes and then connect the lines. Try to draw it symmetric. And then remember that you can't really draw things symmetric. That one's not so bad. This is where we have to be very careful with the language, because in the 1 over x, we're going towards opposite sides of the asymptote, but with 1 over x squared, both sides are going up the, let's not say it that way. Both sides are going up. Let's just say it that way. So our function, I want to do the same kind of thinking up as we did up here. G of x is x to the -2. G prime of x is -2, x to the -3. And G double prime of x is 6x to the -4. Okay. So we see some different stuff happening here. Now, when we look at -2x to the -3, that can be positive and negative. And that makes sense because here, when x is negative, our function is increasing. And when x is positive, our function is decreasing. So here we see those two different signs in G prime. So G prime of x is negative for positive x's and positive for negative x. That tells us about the direction of the function. And that's what we see. It's the derivative is negative for positive x and positive for negative x. God, that's a terrible sentence. The sign of the first derivative tells you about the direction of the function. So we see G is increasing for the negative x, and G is decreasing for the positive x. What we know about the sign of the derivative is reflected in what we see in the graph of the function. When we look at this graph, we can see that the function is always concave up, and we see that reflected in the sign of the second derivative. The second derivative has an even exponent and a positive coefficient. So that means the second derivative is always positive. The second derivative is positive for all x what isn't 0. And so that tells us that g is concave up for all x, for all non-zero x. How's everybody okay? Right. So yesterday I raised the question, how do we move the vertical, move the horizontal and vertical asymptote? If we're going to maintain the shape of this, let's just go with the 1 over x, that hyperbola. If we're going to maintain the shape and we want to just and keep these horizontal and vertical asymptotes, we can do that with a translation by shifting up and down or left and right. So if we want to move the horizontal and vertical asymptotes, we can do that with translations or shift. We can do a shift. A translation, a shift or a translation. Shifts or translations are accomplished with addition or subtraction. So if we modify our inputs and outputs with addition, we're going to produce a shift or translation. Translations are mods that use addition. Horizontal changes happen before the function. Vertical changes happen after the function. Horizontal changes are a result of input changes. Vertical changes are a result of output changes. Horizontal changes are a result of input changes. The vertical changes are a result of output changes. What does that look like in practice? So if I take the 1 over x and I modify the input with x minus c, this is going to shift the vertical asymptote to c. If I modify the output with a plus d, that's going to shift the horizontal asymptote to y equals d. So this plus d Because I'm just taking the whole graph of 1 over x minus c with that horizontal asymptote at 0, and I'm adding d to it. So it's going to shift it up or down. Take the whole graph and shift it up or down. The x minus c, that's going to shift our vertical asymptote, because that's going to change the 0 of the denominator of our rational function. Through addition and subtraction, we shift a graph. If we add or subtract from the input, if we add to the input, we're going to move things left and right. If we add to the output, we move things up and down. Let's look at an example with numbers and then do some algebra stuff. I wrote like, I'm all like rational functions. So everybody's like, oh man, I hope we do some algebra today. You will not be disappointed. So you're hella doing algebra today. This is not how we might normally encounter this particular rational function. But this one lays out clearly what we are going to be looking at. The x minus 1, we can see that we're going to have a vertical asymptote at 1. Because x cannot be 1. And then whatever that fraction is, we're going to add 2 to the whole thing. That's telling us there is a horizontal asymptote at y equals 2. So our vertical asymptote is going to happen at 1. And our horizontal asymptote will happen at y equals 2. And then we just put it in the normal spot. Any questions? How's everybody okay? Now I got to think about variations on this. If I take the x minus 1 and square it, all the stuff that's below 2 will become stuff that's above 2. I don't think I want to do a whole thing. Yikes. So some variations that we're going to want to think about. What happens if I modify this with an x minus 1 squared? So if I do like g of x is 2 plus 1 over x minus 1 squared. So that's just going to make, instead of going opposite sides around our vertical asymptotes, they'll go on the same side. In this case, they'll both go up. That's what we saw when we square, when we have a vertical asymptote from a square factor. Other variations. If I take the part that I'm subtracting, and instead of doing 2 plus this fraction, I do 2 minus this fraction, I'm reflecting the fraction part. So in this case, the negative is going to create a reflection of the fraction part. Multiplying by a -1 produces a reflection. In this case, I've only multiplied the fraction parts by -1. So I'm only reflecting the fraction parts. We still have a vertical asymptote at 1. I only reflected the fraction part, so I still have a horizontal asymptote at 2. But instead of being decreasing on the left and decreasing on the right, we're going to reflect those. I've multiplied the fraction by -1. So instead of 2 plus some fraction when x is greater than 1 and 2 minus some fraction when x is less than 1, I get the opposite. G of x didn't make the yearbook. Didn't show up for picture day. What we want to notice is that when x is less than 1, this fraction part, 1 over x minus 1, is a negative. And so we take 2, that's our flat part, and we're subtracting some fraction. Some fraction that becomes bigger when x gets close to 1, because as our denominator gets close to 0, our fraction gets close to infinity. And so we're taking 2 and we're subtracting some fraction. On the other side, when x is greater than 1, then 1 over x minus 1 is positive. So we have 2 plus some fraction, and that's why it's above the 2. Questions? Comment? Loud remark? When we look at the functions in this form, we want to remember that rational functions are fractions with polynomials. Rational functions are fractions with polynomials. So when we're looking at a function in this form, it's like we're looking at a mixed number. It's like a whole number, 3 2/5. It's like the mixed number 3 2/5. So that is a mixed number. There's a whole number and a fraction part. Presumably the fraction part is less than 1 in the simplified form. Doesn't really have to be. We could call this 2 7/5. That would be the same value, but that would be saying things like 30/12 instead of saying 42. It'd be weird. What is 3 2/5 as an improper fraction? How do I express 3 2/5 as an improper fraction? It's what over 5? 17. Where does the 17 come from? We just add the numbers, but they're fractions, and we only add things that are the same. Sameness in fractions is denominator. So we get a common denominator and then add the fractions. Or we do the shortcut. We do 3 times 5 is 15 plus 2 is 17. And that gives us our improper fraction form. And also, we realize that we didn't leave ourselves enough space. By we, I mean me. So we take the 3 2/5 and we just kind of like go around like this, where we multiply here and we add here. 5 times 3 plus 2 over 5. If we want to do that with this function, if I want to take this mixed number form and write an improper fraction form, I can just do the same thing. Start down here and I can multiply and add. I'll have 2 times x minus 1 plus 1 over x minus 1. And then I simplify this as 2x minus 2 plus 1. So 2x minus 1 over x minus 1. So 2x minus 1 over x minus 1 is the same function as 2 over 1, 2 plus 1 over x minus 1, in the same way that 3 2/5 is the same as 17/5. In this case, we can still see that vertical asymptote at x equals 1. The horizontal asymptote, we have to think about what's happening as x goes to infinity. And as x goes to infinity, these minus 1s don't matter. 2x divided by x is 2. 2 billion divided by a billion is 2 billion. 200 billion divided by 100 billion is 2. The minus 1 doesn't matter. So we would think about it slightly differently. We would still look at this and say there's a vertical asymptote at x equals 1. But then when we look at the limits, we have to think about what's happening as x goes to infinity. And as x goes to infinity, this all goes to 2. Same horizontal asymptote that we had before. Any questions? So even though we're using polynomials in our mixed numbers, the operation is the same as we learned way back in arithmetic. I wanted to go back. So this is how we take a mixed number and write it as an improper fraction. How do I write an improper fraction as a mixed number? How do I go this way? We have 17 over 5. How do I write that as a mixed number? The fun part is it just tells you what to do. 17 over 5 means 17 divided by 5, so we just divide. And at this point, we're like, oh, how many times can we subtract 5 from 17 without going negative? How many times is that? 2. 2 times 5 is 10. 17 minus 10 is 7. Oh, shit, it's more than 2. How many times can I do it? 3. Oh, shit, let's just subtract another one. See, you can't fuck it up. If we allow things like negative numbers, we can't mess it up. If you miss low, you'll see that you can, oh, I could subtract another 5. Here I am subtracting 2 5s, but I could have subtracted 3 5s right from the get-go. Just keep going, just subtract another 5. Does that make sense? That's what division is about. Subtracting, it's just subtracting. Multiplication is just addition, division is just subtracting. With like the 0 thing. Makes the 0 thing make more sense. How many times can we subtract 0 from 17? Yeah. Infinitely many, I guess. I don't know. But since you're kids, we're just like, oh, you can't do it. You're like, oh, but what if, shut up, you can't do it. All right. Why am I scared now? Because I'm a math teacher. So I have to teach here because y'all don't go trick-or-treating. So I'll still get trick-or-treaters at my house. Eventually someone will come by my house and go, oh shit, it's a math teacher. And all the kids will like run screaming down. Like, you think it's like scary that Jason has a hockey mask and a machete, right? Like with a whiteboard marker and a quiz. Show your work. This is why I have to give out full-size bars. So this is the 2 left over, and I can no longer subtract 5 from 2 without going negative. So I might have written like 2 7/5. It's like, oh, well, that's not how we normally call that number. That's not what we say. We say 3 2/5. You can't mess it up. What if we do? It's also just fun to mess it up sometimes. Let's subtract 4 5s from 17. You're like, oh, let's subtract 4 5s from 17. What's 4 times 5? It's 20. If we subtract 4 5s from 17, what are we left with? -3, right? At this point, we're like, oh, whoops, fucked up. But not really. Because instead of just saying, instead of going back and trying to fix things, it's like, oh, well, this is just 4 3/5. That'd be like referring to 27 as 30 -3. We don't call 27 30 -3. But if you're in your 20s, I'm sorry to say, you are also in your 30s. If you're 22, you're 30 -8. But if we write 4 and -3/5, the reason that this is confusing is that we don't normally write the plus. We just take the mixed number and we just jam the 2 parts together. That was one of the worst decisions we ever made. It's like, well, it'll make sense. It's like, well, you know, we do the same thing for multiplication, just jam shit together. It's like, oh, people will know. Hundreds of years later, people don't know. But 4 and -3/5, if I subtract 4 and -3/5, well, shit, that's 4 times 5 is 20. But subtract 3 this time. Still 17/5. So 4 and -3/5 is not the way we normally write 17/5. 4 minus 3/5 is going to be 3. I spelled 3 wrong. So why it's important to be flexible. That's like 3 plus 2/5. Take 5 of the 5/5 from the 4 and stick them on the fraction. -3/5 plus 5/5 is positive 2/5. You can't mess it up. Incidentally, if you want to have 2x minus 1 over x minus 1, you want this mixed number thing so you could see things more clearly. You do the same thing. You just do division. 2 plus 1 over x minus 1. Same thing. Algebra was arithmetic the whole time. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing.